Okay, welcome back. In this video, we will discuss about divergence theorem and Stoke's theorem. Let us start with divergence theorem. Okay, so let me write the definition of divergence theorem, which says that for any vector function that is continuous, okay, meaning that it's smooth and differentiable over some region in space of volume V. Okay, I think I'll just write volume V. The volume integral of del dot E is, okay, for any vector function, let's say E, the volume integral of del dot E is equal to the surface integral of E over the surface S that bounds the volume V. Okay, so I understand this is not an easy definition, but I'll try to simplify it. So it's saying that for any vector function E, when the volume integral of del dot E, so you take del dot E, the divergence of E, and you calculate the volume integral. Okay, so this is how you calculate the volume integral. Okay, and the divergence theorem tells that that should be equivalent to the surface integral of E dot ds, that is the surface integral of E over the surface. So this should be a surface integral on this side. However, this surface should be a surface that bounds the volume. Okay, so this cannot be any arbitrary surface. No, this surface should be a surface that bounds this volume. Let me write this over here. This surface should bound volume B. That's why we put a notation for a closed surface. Okay, let me give an example. Okay, let me draw okay, let me put in a problem and then tell you about the closed surface. Okay, this is an example one for today, and it says there is a given vector function A equals to x square ax plus xy ay hat plus yg az hat. Okay, and you have to verify the divergence theorem over a cube with sides of unit length Okay, to simplify, we'll tell that one corner of cube is at origin and other is at 1 comma 1 comma 1. Okay, let me draw that cube over here. And I am sorry, I want to use a different color. Delete, use a different color. Okay, let us draw that cube again. Okay, there is a cube, and I select this, copy, paste that cube, take it somewhere over there. Okay, that is our cube. Okay, and of course, so this starts over there at 0 comma 0 comma 0, and let's say the other is at 1 comma 1 comma 1, and of course this cube encloses some volume v, right? But that volume is being enclosed by the 6 faces of the cube. Okay, let me label them. So the first face could be this front face, the other face could be the back face, the other face, okay, let me have this somewhere over here. Okay, this is our front face, that's our okay, and have that on the back because that is a back face. Okay, and we have another face which is the top face, we have the bottom face, we have the right of another face on the right side, and finally one more on the left side. So these 6 faces of the cube are bounding that volume, right? So when you consider the divergence theorem, then your surface has to be these 6 faces, because those 6 faces are the surfaces that are bounding the volume V, which is the volume of the cube. Okay, that is what we mean by the surface. When I write over here, the surface should bound the volume V. Okay, I hope that helps. And now, okay, so I'll give you I'll let you work on this problem, and you can calculate. Okay, let me give some hints. You can calculate del dot E, the divergence of E, and you can of course take the volume integral with respect to dv. Okay, that is fine. And then for the other side, for the right hand side of the equation, you have to calculate E dot ds for each faces. So that one will be for the top. You have to calculate again E dot ds for the bottom face, and E dot ds for the top face, again E dot ds for the bottom, E dot ds for the right, and finally E dot ds for the left, and your final E dot ds will be the sum of these 6 faces. Okay, and that result should be equivalent to this result that you calculated from the left hand side of the divergence theorem. And one more thing again to remind you, this ds over here, this is a vector differential surface. In other words, that is ds times an, where an is called the unit normal vector, and for a closed uh, surface like this, okay, or for if your surface is bounding a volume, then your an points away from the volume, okay, meaning that for this face number 3 it has to point away from the volume. For this face number 4 it has to point downwards because that is the direction away from the volume, and so on, right? So you should be able to work on this problem, and we'll discuss another theorem, which is Stoke's theorem. Okay, and Stoke's theorem, similar to divergence theorem. Let me write the equation. It says E dot dl equals to del cross E, or usually let me write that del cross E on the other side. Del cross E dot ds integral surface integral equals to E dot dl. So it's saying that, so on this side you see the surface integral of the call, and that should be equals to circulation of the field along the boundary. And there's a catch: this boundary encloses the surface. Okay, to give you an example, okay, let's say this is your surface. Okay, this is our surface, and you are calculating the surface integral. Okay, there's a vector function, you are calculating the surface integral of the call, and this surface over here is being bounded by this contour or by this boundary. Okay, this has to be that boundary, and this has to be this surface. Okay, it cannot be this surface and some other boundary. It has to be the boundary that encloses the surface. And similar to the divergence theorem, let's work on a problem for Stoke's theorem. Okay, and I'll use one of the problem that we are familiar with, and the problem says given a vector equals to xy ax minus 2x ay, verify Stoke's theorem over a quarter disk with radius 3 in the first quadrant. Okay, so for this problem you will calculate del cross A, and then you'll calculate the surface integral okay, which is the left side of the Stokes theorem. Okay, and you are given a surface something like that. That is your first quadrant. This circle has, or quarter disk has radius 3. Okay, and here contour defining the surface will be this part of the disk, that part of the disk, and this part of the disk. So all right, so you'll calculate the this E dot dl for these three different part, and you'll combine them together to check whether you get the result that you obtained from the left hand side of the Stokes theorem. Okay, please work on this problem and let me know if you have any confusion or if you have any difficulties, and if there is any way I can help you to understand more about the the divergence theorem or the Stokes theorem. And by the way, this divergence theorem is also sometimes called as Gauss divergence theorem. Okay, with that, I'll sign off in this video and see you in the next one.